When ad agencies are designing a marketing campaign, they sometimes have to work backwards, starting with the end result and creating a scheme that will attract attention from the beginning. This process has a mathematical name that we will be investigating in today's lesson. Hi, my name is Jason Rosenberry. Let's begin by looking at a theorem. The mean value theorem connects the average rate of change of a function over an interval to the instantaneous rate of change of the function at a point in the interval. Let's take a look at it. Theorem 3, the mean value theorem. If y equals f of x is continuous at every point of the closed interval a to b and differentiable at every point of its interior a to b, then there's at least one point c in the interval from a to b at which f prime of c equals f of b minus f of a over b minus a. Let's look at an illustration of this theorem. The blue curve represents the graph of f of x. The mean value theorem is an existence theorem. It tells us that the number c exists without telling us how to find it. The real importance of this theorem lies in the conclusions we can draw from it. For instance, again looking at the picture, blue curve represents f of x. What this theorem is saying is that on the closed interval from a to b, so here we are at x equals a, here we are at x equals b, so the segment AB is a secant. It's intersecting the graph at two places. Well, that secant would have a slope found by using your difference quotient. What this theorem is saying is that between a and b, somewhere must exist this value c such that the slope of the tangent line at c is equal to the slope of the secant from a to b. Let's try an example. Let f of x equal the square root of 1 minus x squared. Let point A be the point negative 1 f of negative 1 and point B be the point 1 f of 1. Find a tangent to f in the interval negative 1 to 1 that is parallel to the secant AB. From the graph we see that f is continuous on the closed interval from x equals negative 1 to x equals positive 1. F prime, the derivative of f, is defined on the open interval negative 1 to 1 and is not defined at negative 1 and 1. We can use the mean value theorem. We see that at f of negative 1 and also at f of 1, function value is 0. So here we are at this point, negative 1, 0, and also f of 1 is 0. So here we are at the point 1, 0. The slope of the secant line through those 2 points, using your slope formula, we would get a slope of 0. It's a horizontal line. The mean value theorem says that there must be this point C somewhere between x equals negative 1 and x equals positive 1 such that the slope of the tangent line is also 0, meaning another horizontal line, or in this case a horizontal tangent line, and we can see that up here at this point there would exist a horizontal tangent line, and that value occurs at x equals 0. We can physically interpret the mean value theorem as saying that the instantaneous rate of change at some interior point must equal the average rate of change over the entire interval. A trucker handed in a ticket at a toll booth showing that in 2 hours she had covered 159 miles on a toll road with a speed limit of 65 miles per hour. The trucker was cited for speeding. Why? Well, let's start by finding her average speed. We know that she traveled 159 miles in 2 hours. So this would translate 159 divided by 2 is 79.5 miles per hour. That's her average speed. But, however, according to the mean value theorem, there must have been a moment in between where her instantaneous speed or instantaneous rate of change was the same number. So there had to be a moment somewhere in her travels where she actually traveled 79.5 miles per hour. We can also use the mean value theorem to determine where a function is increasing or decreasing. Let's start with a definition. Increasing function, decreasing function. Let f be a function defined on an interval I, and let x sub 1 and x sub 2 be any 2 points in I. 1. F increases on I if x sub 1 being less than x sub 2 implies that f of x sub 1 is less than f of x sub 2. Or 2. F decreases on I if x sub 1 less than x sub 2 implies f of x sub 1 is greater than f of x sub 2. With these definitions, we can use the mean value theorem to use the derivative to determine intervals of increasing and decreasing. Corollary 1. Increasing and decreasing functions. Let f be a continuous function on the closed interval from a to b and differentiable on a to b. If the derivative of f is positive at each point of a to b, then f is increasing on a to b. If the derivative is negative at each point of a to b, then f decreases on a to b. Let's try some examples. Use analytic methods to find a, the local extrema, b, the intervals on which the function is increasing, c, the intervals on which the function is decreasing. And let's say that we're given f of x equals 5x minus x squared. So here's our function f of x equals 5x minus x squared. And to find the extrema, let's go ahead and find the derivative. So f prime of x would equal, the derivative of 5x is 5, and the derivative of negative x squared is negative 2x. Now we'll set this derivative equal to 0 and solve for x. So we have 0 equals 5 minus 2x, which implies that 2x equals 5, and that implies that x is equal to 5 halves. So we have either a local max or a local min at x equals 5 halves. Now let's go ahead and take a look at the graph of f of x. So here's the graph of 5x minus x squared. We have a parabola that opens downward, and that we can see that at x equals 5 halves, which is 2.5, we can see that we have a maximum value of, and a way of getting that value would be to substitute 5 halves back into the function, and f of 5 halves is 25 fourths. So we can see that there is a maximum value of 25 fourths at x equals 5 halves. The domain of f is all real numbers, or from negative infinity to positive infinity. And we can see that f increases on the interval from negative infinity to that vertex, 5 halves. And then f decreases on the interval from 5 halves to positive infinity. Use analytic methods to find a, the local extrema, b, the intervals on which the function is increasing, c, the intervals on which the function is decreasing. Your function is h of x equals negative x over x squared plus 4. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So here's our function h of x equals negative x over x squared plus 4. Let's begin by finding the derivative of function h. So h prime will equal denominator x squared plus 4 times the derivative of the numerator, derivative of negative x would be negative 1, minus the numerator negative x times the derivative of the denominator, which would be 2x. All of that over denominator squared, or x squared plus 4, the quantity squared. Now let's simplify. So h prime of x would equal, in the numerator, we'll distribute the negative through the quantity x squared plus 4, giving us negative x squared minus 4. And when we multiply all of this together, we get a positive 2x squared. All of that over denominator squared. So we have x squared plus 4 squared. And this simplifies to combining like terms. We get x squared minus 4 over the quantity x squared plus 4 squared. And we can see that the numerator is difference of squares, so we could factor that to x plus 2, x minus 2, all over x squared plus 4, the quantity squared. So there's our derivative. Now that we have our derivative, we want to find critical points, values of x that cause the numerator or denominator to equal 0. Making denominator equal 0 implies values of x that cause the derivative to not exist. So obviously in the numerator, we can see that there are two values that would cause the numerator to equal 0 to negative 2. So we have some critical values of plus or minus 2. The denominator we cannot make equal to 0. Therefore, there are no values of x that cause the derivative to not exist. So we've identified two critical values, positive 2, negative 2. And now we'll use the graph of h of x to see if we have local min values or local max values at positive 2, negative 2. And we'll also use the graph to see where the function is increasing and also decreasing. So here's the graph of h of x, and as we can see, at positive x equals 2, we have a local minimum value, and at x equals negative 2, we have a local maximum value. Also looking at the graph, we can see that this function is increasing on two intervals. This function is increasing from negative infinity to negative 2, negative infinity to negative 2, and it's also increasing from positive 2 to positive infinity. Positive 2 to positive infinity. The function is decreasing where the function is decreasing from negative 2 to positive 2. The coordinates of the actual max value and the min value can be found by evaluating function h at negative 2 and positive 2. So we would get the actual max value of being positive 1/4 and the min value to be negative 1/4. Now let's move on to two consequences of the mean value theorem that are related to each other. Corollary 3, functions with the same derivative differ by a constant. If f prime of x equals g prime of x at each point of an interval I, then there is a constant c such that f of x equals g of x plus c for all x in I. Let's try an example. Find the function with the given derivative whose graph passes through the point P. Let's say we're told that f prime of x, the derivative of f, evaluated using x, is equal to negative 1 over x squared. We're told x is positive and point P is the point 2, 1. We want to try to find the function that passes through the given point 2, 1 that also has the derivative f prime. So here's our derivative. F prime of x is equal to negative 1 over x squared. We have x greater than 0, and we have the point P being at the location 2, 1. So now we want to find function f that has a derivative of f prime of x and also passes through the point 2, 1. So we've had enough experience in the past to know that 1 over x that term's derivative would be negative 1 over x squared. So function f, the first term of this function, we could write 1 over x. Why? Because the derivative of 1 over x is negative 1 over x squared plus some constant c. Now we have to find out that constant c by evaluating our function f using the point 2, 1. So we know that f of 2 is equal to 1. So 1 equals 1 over x would have to equal 2 plus c. Now solving for c, we subtract 1/2 from both sides, giving us c is equal to 1/2. So now making that substitution into our function f, we have f of x would equal 1 over x plus 1/2. That is the function that has derivative f prime of x, and also the point 2, 1 satisfies this function as well. The function we found to answer the question in that example has a name. It is called an antiderivative. Let's define that now. Antiderivative. A function capital F of x is an antiderivative of a function f of x if capital F prime of x equals f of x for all x in the domain of f. The process of finding an antiderivative is antidifferentiation. Let's antidifferentiate. On the moon, the acceleration due to gravity is 1.6 meters per second squared. Part A, if a rock is dropped into a crevice, how fast will it be going just before the bottom 30 seconds later? Well, we're told in the problem that acceleration is 1.6 meters per second squared. So we have our acceleration function. We know that a of t is 1.6. Notice part A is asking for how fast will this rock be traveling. That's implying velocity. We know that the derivative of velocity is acceleration, so we want to go in reverse. What function out there has 1.6 as its derivative? So the velocity function v of t would equal 1.6t. Its derivative is 1.6. So we also know this has to differ by a constant c. We also know that we're falling from rest. So we know that the velocity function evaluated at 0 must be 0. So that implies that our constant function must be 0. So c is 0. We put that all together. We now have our velocity function v of t equals 1.6t, and now we'll evaluate that velocity function using 30. So v of 30 is equal to 1.6 times 30, or 48, and the units would be meters per second. So the velocity, 48 meters per second. Part B, how far below the point of release is the bottom of the crevice? So we know that our velocity function, v of t, is 1.6t. We know that the antiderivative of velocity would be the position function. So let's find the position function s of t. So we're trying to find a function s of t whose derivative is 1.6t. Well, we know that 0.8t squared. We know that the derivative of 0.8t squared would give us 1.6t. So we know that the position function s of t is equal to 0.8t squared plus some constant c. We're told in the problem that the object is falling from rest. So that implies that s of 0 must give us 0. So that tells us that c, our constant, must equal 0. So making that substitution gives us our position function s of t is 0.8 t squared. So now to solve the problem, let's evaluate our position function s at 30. So we evaluate 0.8 times 30 squared, and that gives us 720, and the units would be meters. So the answer to part B, 720 meters. Part C, if instead of being released from rest, the rock is thrown into the crevice from the same point with a downward velocity of 4 meters per second, when will it hit the bottom and how fast will it be going when it does? Let's start this part by finding our velocity function and our position function. From a previous part, we know that our velocity function is 1.6 t plus some constant. So we're told in the problem that the velocity will be 4 meters per second at time 0. So that tells us that v of 0 is 4. So 4 is equal to 1.6 times 0 plus c. This implies that c must equal 4. So now we know that our velocity function, v of t, is 1.6 t plus 4. Now, using our new velocity function, let's find the position function, s of t. We know that the derivative of s of t is v of t. So again, working in reverse, our position function will be 0.8 t squared plus 4t plus some constant. And again, we're throwing this rock from rest, so s of 0 is 0. So at time 0, the position would be 0. So that tells us that our constant must be 0. So our position function is s of t equals 0.8 t squared plus 4t. From part B, we know that the distance that this rock is traveling to the bottom is 720 meters. So let's set our position function equal to 720. So we have 720 is equal to 0.8 t squared plus 4t. And when we solve this equation for t is approximately equal to 27.604. So we've answered the first question. When will it hit bottom? That's going to happen approximately 27.6 seconds upon release. The follow-up question is, how fast will it be going? Well, since we have our t value, let's now plug our t value into the velocity function. So v of, evaluating our function v at 27.604, taking 1.6 times that value plus 4, it's approximately equal to 48.166. So the velocity would be 48.166 meters per second. In this lesson, we explored how to determine when the graphs of functions are increasing and decreasing, as well as anti-differentiation. Be sure to work the exercises that your teacher assigns, and we'll see you next time.